So is this a math circle in Stanford? Or
no, not exactly. It's a separate virtual math circle I'm trying to run because of the COVID-19 thing specifically. So a few people seem to be joining now. Hello, all who have just joined. We'll be getting started.
Okay. Let me get back in 1 minute. Okay.
Okay, no problem. We will be getting started soon-ish. We'll be waiting a few minutes after 5, just for people who are late to trickle in. And after that, we'll be getting started.
Okay.
So we're going to wait another minute or two.
Sure.
Because a few people usually trickle in a little late. And we'll get started. So,
yeah, just let me know. I'm going to write subtitle or something.
Awesome. So to everyone who's here, just to make sure everyone's familiar with it, you should be able to access the chat by clicking something at the bottom of the screen. And then you can also raise your hand by clicking on the participants button. And then there should be some way to do something, but I can never figure that one out sometimes. But in any case, you should at least be able to ask questions in the chat.
Okay. Yeah, I opened the chat, so I'll probably will see the messages immediately. And I can also see the list of participants.
Great, so let's get started in about 1 or 2 minutes.
Sure.
All right, so thank you all for coming. Dr. Ilya Kachkovskiy, I might have mispronounced that, and if so, my apologies.
That's okay.
We'll be giving a talk today
Close enough.
on difference equations, so I'll hand it over to you to start it off.
Okay, so thank you very much. Thank you very much for inviting me. I hope you can hear me well. This talk is about difference equations, and it looks like something. I mean, okay, it's something that looks like maybe more of a high school material, but apparently these days people are studying more advanced questions in the context of quantum solid state physics, and sometimes they explain the problem better than the usual differential equations. So This is not completely unrelated to modern research, although, and I'm part of my work is about this, but I'm not going to talk about it. I'll talk about more basic stuff. All right, so let me first start from some motivation. The motivation is from Fibonacci numbers. It's a well-known sequence of numbers. I'm sure that most of you have seen it before. It starts from 1. Next number is 1, and 2, 3, 5. And I guess you can guess that the rule is the following, that to get the next number, you add 2 previous numbers. So the next number is going to be 8, because 3 plus 5 is 8. And the next number is going to be 5 plus 8, which is 13. 21. And so on. You can continue the sequence infinitely. And there are a lot of problems related to the sequence. There are books written about it. It's very famous. And we're going to suggest some theory which will allow you to derive a general formula for terms of the sequence and some other sequences. All right. First, let's make this question a little bit more formal. Let's actually, instead of starting from 1, let's start from 0. So let's denote the 0th Fibonacci number by 0, and then you can apply the same rule. This 1 is obtained from 0 and 1, 2 is obtained from 1 and 1, it's the same thing. You can write it also like this. Denote by Fn, nth Fibonacci number. Then you can define them formally by the following system of equations. F0 equals 0, F1 equals 1, and Fn plus 1 equals Fn plus Fn minus 1. All right, and once these 3 rules are satisfied, starting from 0 and 1, you can find F2. Using F1 and F2, you can find F3. Using F2 and F3, you can find F4 and so on. You can generate these numbers one by one, and you will always be able to find out the next number. So these equations uniquely define Fibonacci sequence. So these equations uniquely determine Fibonacci sequence. And by the way, using these equations, you can also define Fibonacci numbers with negative indices by, for example, if you take, let's for example find f minus 1. We can just plug n equals 0 in this equation and get f1 equals f0 plus f negative 1. Right, and f1 is 1, f0 is 0, so f minus 1 equals 1. Let's also find f minus 2 to demonstrate that there is something different. f0 equals f minus 1 plus f minus 2, which means that, okay, 0 equals 1 plus f negative 2. So f negative 2 equals negative 1. Okay, so I'm not going to go there, but basically, if you extend the sequence to these negative numbers, it also extends uniquely using these rules, and you'll just get the same Fibonacci numbers, but some of them will have a minus sign. There will be interchanges plus or minus sign. That's not very interesting. All right, let me also introduce some more terminology. I will call this difference equation. Okay, I don't know if it's a good wording, but it's kind of to compare it with differential equations. But I don't know how many of you know differential equations, so for you this might be meaningless. You can also say it's a recurrent sequence. Recurrence equations, let's say. And this is what we're going to call initial data. So to find Fibonacci number, we need to know where do you start, what are the first two Fibonacci numbers, and then you need a law that generates next number based on the previous two. So if you just have the law but don't know where to start from, you cannot find the numbers. And for example, if you just have this F0 but don't have a fund, it's also not enough data to completely determine Fibonacci numbers. So usually we need two components. We need some equation and we need some initial data. All right, so let's, before going into this formula, I think, let's do some quick exercise to warm up. Let's find this. F0 plus F1 plus Fn. So is there any formula for this? You can use Fibonacci numbers, but you don't want to use this summation symbol. Okay. Yeah, so let me just tell you the answer. I don't know if I should leave this as an exercise, but just as an introduction, I'll just tell you the solution. So let's write down F0 equals F2 minus F1. Right? If you move F1 to the left-hand side, you'll just get the original equation. F0 plus F1 equals F2. F1 equals F3 minus F2. 2 equals F4 minus F3. I just take equation for each Fibonacci number and move Fn into the left-hand side. Okay, and I can do it for any number. Yeah, by the way, if you have any questions, make sure to interrupt me at any moment. I don't have any specific, I have a few topics I want to discuss, but I don't have any specific plans, so I can slow down at any moment. I'll give more detail. All right, and let's do it until Fn. Fn plus 2 minus Fn minus 1. All right, so we have a lot of these equations, and then the idea is that we can just add them together. Yeah, question?
Oh, I was just going to interrupt to say I just wanted to see, to pause for a moment to see if anyone knew where this was going to go just before you reach the conclusion, just to make sure if you want to understand it.
Oh, say it again, please.
Oh, I just wanted to interrupt to check if everyone knew based on this, how to compute this sum. So if anyone knows how to do it, just pop it in the chat right now.
Yeah, I can wait. I can wait 1 minute. Yeah, you can put the answer if you can. From this calculation, if you can see the answer, put it in the chat. You can use Fibonacci numbers as the answer. The goal is to avoid the adding unknown number of terms. I just want some kind of closed form expression. I'll wait 30 more seconds, and I'll continue. Yes, I got the correct answer from someone. Okay, first answer was correct. The one that said privately from D. This Fn plus 1 is almost correct. I think part of the reason is that I had a typo here. Okay. So let's add all these equations. Then on the left-hand side, we get F0 plus F1 plus Fn, which is what we want to find. On the right-hand side, we'll get something interesting because you get F2 minus F1, F3 minus F2, plus F n plus 2 minus F n plus 1. Okay, and now what do you see? If you open the brackets, a lot of this number is going to cancel. For example, F2 cancels here. If you look at the next term, this F3 will cancel with F3 from the next bracket. In fact, everything is going to cancel. Okay, I did the same mistake again, n plus 1. Everything is going to cancel except for the very last number and the very first number. Equals, after cancellations, Fn plus 2 minus F1. Which is, you can simplify this because you know what F1 is. F1 equals 1. Yes, correct. The chat got the right answer. Fn plus 2 minus 1. Okay, that was just an exercise. In fact, right now, I'm actually switched from Fibonacci numbers to some other sequence because the calculation that I want to do is simpler for that sequence. So then we will develop a method and then apply it to Fibonacci numbers. All right, new sequence. Okay, any questions about this calculation? I hope it's clear. So I got a few correct answers in chat, probably it's clear. Okay. Example of a different equation. Another difference equation. Okay, let's denote it by a different letter. Let's say U n plus 1 equals UN plus U plus 2U n minus 1. Okay, this equation is not enough to find sequence U because we also need initial data. We need somewhere to start. But let me not specify the initial data. So the idea to solve this equation is that first you look only at the equation, then it has a lot of different solutions, but you try to describe all possible solutions. And once you find all possible solutions, then you find those that match initial data. So plan. Okay, actually, let's do initial data. Do you want to do initial data? Let's say, okay, let's do U0 equals U1 equals 1. Plan. First, forget about initial data and try to find as many solutions of the equation as possible. Let's mark this equation by 1. As many solutions of 1 as possible. 2. And if we are lucky, x squared minus x minus 1. Okay, yeah, I already see some people. Yeah, so I'm going to talk about characteristic polynomial. I don't know if you're familiar with this or not, but yeah, if you do it, you need to use characteristic polynomial. That's correct. So, but I don't know how many of you know about it, so I'm still going to tell about it. Yeah, so forget about initial data and find as many solutions of equation 1 as possible. And once you do it, if we're lucky, so we'll find solutions from previous part matching initial data. Okay, and how do we look for solutions? Well, there is some theory behind it, which is linear algebra, but it's a bit advanced. And first people who found it probably didn't use linear algebra. They just were trying to guess. And we will try to guess the solution in the form of geometric series. So try to guess solutions of 1 as a geometric series. Okay, let's try to take the most simple geometric series, un equals lambda to the power n, where lambda is some number. Yeah, you already, yeah, this is the correct answer, but I still have to arrive to it. Okay, un equals lambda to the n. Right, so then if you, let me copy the equation. If you want this equation to be true, then you want lambda to the n plus 1 equals lambda to the n to lambda n minus 1. N minus 1. And if you factor out lambda to the n minus 1, we get lambda squared minus lambda minus 2 equals 0. All right. And if you want this to be equal 0, one obvious way is to make lambda to be 0, but that's not very interesting because if you take all un equals 0, there's going to be a solution. So we will try to look lambda that solve this equation. Then it's going to be lambda equals 1 plus or minus. I hope you can solve quadratic equations. Yeah, one person already told me the answer is 1 plus or minus square root 1 plus 8 divided by 2 plus or minus 3 divided by 2. So there are two solutions. Lambda 1 equals 1 plus 3 divided by 2 is 2. 2 is negative 1. Okay, which means that we have two of the following, let's call it basic solutions. Basic solutions. First one will be sequence 2 to the n. Second one will be sequence -1 to the n. And of course, these are not all possible solutions. For example, if you take 2 to the n multiplied by any constant, let's say 10, still going to be a solution. And if you add these two things together, because this is a linear equation, there's some also going to be a solution. In general, any sequence of the form un equals a times 2 to the n plus b times -1 to the n solves the equation. Solves the equation let me copy it. Okay. Sorry, some glitch. All right. And you can also prove that there are no more solutions, that any solution of this equation will be of this form, though it's a little bit harder. Okay, now let's remember about initial conditions. Q0 equals U1 equals 1. If you don't have initial conditions, then you can put any number, say, in B, and there's going to be a solution. Yeah, thanks. Yeah, someone already, yeah, again, D sent me a private message with the answer. Let's check if it's correct. Yes. If we have initial conditions, we can try to plug these conditions into this general formula and find what exactly A and B we should have. And U0 equals 1 gives us equation n equals 0. A plus B equals 1. Okay. And second equation, okay, so can someone besides D write in the chat the second equation? Any person. So if we take n equals 1 and require un to be equal to 1. What? Yeah, okay, so 2a minus b equals 1. Yes, that's correct. Thank you very much. 2a minus b equals 1. And if we solve the system of equations, for example, we can add them, get 3a equals 2, a equals 2/3, and using the first equation, b equals 1/3. Yes, that's the same answer as these. All right, and finally, answer is un equals 2/3 2 to the n, 1/3 minus 1 to the n. Okay, and you can check that it actually satisfies both equation and initial conditions, but yeah, you can check it.
So I just want to pause for a moment here, and you said you talked about proving that those are all solutions. So I just want to see if anyone here, because it's pretty close to it from what we've described so far. I want to see if anyone either wants to unmute themselves or say in chat just to provide a quick explanation of why those are all solutions to the equation above.
Oh yeah, please. Yeah, if someone have a simple explanation for this. Yeah, it's not very hard. Yeah. Do you have a timer on this?
I don't think there is anything.
Let's wait 1 minute from now. If someone wants to say something.
So just go ahead and unmute yourself if you know how to do it, or
yeah.
you can type it in the chat. Either way is fine.
Okay. Any volunteers? Okay, so what would you prefer? Do you prefer me to tell you, or to leave it as a homework?
Maybe we should try continuing on, and then if it's still relevant later, we can see.
Yeah, okay, let's get back to this question later then. All right. So this was the example of this. Oh, for the question is, why is every solution of the difference equation, of this equation, can be represented in this form? Okay, but let's get back to it later. In the end, we can talk about it again. Let's now get back to the Fibonacci numbers. The reason I started with this example is because the quadratic equation doesn't have any square roots in it, so it's a little bit simpler to understand. And the same method works for Fibonacci numbers. So let's remind ourselves f0 equals 0, f1 equals 1, fn plus 1, fn, fn minus 1. All right, and let's use the same method. Let's try to find the same method. So we first forget about the initial data and only look at the equation. Okay, so yeah, so someone sent me the solution that is unique. I think it's correct, but I suggest we talk about it in the end. Okay, let's just look at this equation again and forget about the initial conditions. Then we can try to do the same thing. Try to look for solutions. Lambda to the n, which will give you the equation lambda n plus 1 equals lambda n minus 1. And if you factor out lambda n minus 1, lambda squared minus lambda plus 1 equals 0. And again, if we put lambda equals 0, this is not interesting. Otherwise, we have to satisfy this equation, which means we have to solve the quadratic equation. Lambda squared minus lambda minus 1 equals 0. Lambda equals 1 plus minus square root of 5, 1 plus 4 divided by 2. And therefore, we have two solutions. They actually have the special names, special notation. Phi equals 1 plus square root of 5 divided by 2. And psi equals 1 minus square root of 5 divided by 2. And phi is so-called golden ratio. Psi, I think it's called inverse golden ratio. And I have a typo, right? I have square root of 5. So the reason why it's called inverse, because phi times psi. What is 5 times psi? Can someone tell me?
1.
1. Yeah, thanks. Negative 1. Right? You can see just by multiplying and using the formula of a minus b times a plus b in the numerator, or you can use the Vieta theorem, the product of roots of the quadratic equation equals negative 1. So phi and psi are mutually inverse up to a minus. So psi is negative inverse of phi. I know sometimes people call negative psi inverse golden ratio. Actually, not very familiar with terminology. Anyway, by the same logic, the most general form of the solution, so the most general solution of the Fibonacci equation, copy, paste, is well, so we didn't prove it completely, but at least we didn't prove it yet that it's the most general solution, but at least we have a lot of solutions of the following form. A times phi to the n plus b times psi to the n. Okay, and now let's try to satisfy the equation, the initial data. So we have to say if 0 equals 0, if 1 equals 1. What is the system of equations that we're going to get? Can someone type in the chat? You can start from first equation. Okay, a plus b equals 0. That's correct. And a phi plus b inverse phi, which is psi, equals 1. Yes. A phi b psi equals 1. Let's rewrite the second equation in the following form. So a plus b equals 0, and a plus root 5 over 2 plus b 1 minus root 5 over 2 equals 1. And here, if you look, you'll have a plus b, which using the first equation is 0. We can simplify it more. A plus B equals 0. A root 5 over 2 minus B root 5 over 2 equals 1. Okay. I guess, yeah, A equals 1 over square root of 5, B equals negative 1 over square root of 5. Yeah, that sounds about right. Someone told me the solution. So we have B equals negative A from first equation. Let's plug it to the second equation. Okay, A root 5 over 2 plus A root 5 over 2 equals 1, which means that A equals 1 over root 5. And because B is negative A, B is negative 1 over root 5. Yeah, thank you for the private message. All right, and then finally we can come up with the answer. Fn equals root 5 phi n minus psi n. And you can also write it more explicitly. 1 plus root 5 over 2 n minus 1 minus root 5 to n divided by root 5. Okay, this is the first goal of this lecture, to derive this formula. And I don't know, when I learned this formula, I was pretty impressed that you can write down any Fibonacci number using some algebraic operations without any recurrence. And it's also really, really interesting. Well, when I learned this formula, that it has these roots of 5. Fibonacci numbers are integers, of course, but the final formula for them contains root of 5. Well, the reason is that if you calculate this nth power by binomial formula, then all terms in the numerator that do not have root 5 will cancel. Because if root 5 is in even power, then it's just going to have here with plus, here with minus. The terms will, yeah, this is called Binet formula. That's correct. Yes. I'm not sure. I think it's called Binet. Yeah. Binet or Binets. I'm not actually sure about spelling. I'm too lazy to look in the Wikipedia. Okay. Root 5 will eventually cancel. All right. This is kind of a simple case of a difference equation. Let me give you another example, which let's do another example. Yes, I know some of you might have seen this before. Let's consider the equation un plus 1 equals 4 un minus 4. For un minus 1, sorry. And similarly, it's a difference equation of really the same type. You need to specify initial conditions and then find a general formula for u. And let's again do some simple initial conditions. U0 equals 1, U1 equals 1. Okay, so let's try to solve it. Okay, so let's try to do it the same way as we did previous problem, using the quadratic equation. So can someone write down the equation that we get for lambda, the quadratic equation. Yeah, correct. Lambda squared minus 4 lambda plus 4 equals 0. And if you try to solve it, well, that's easy one. You get lambda minus 2 squared equals 0. Use lambda equals 2. Yes, so there is only one root 2, and which means that you have a solution un equals 2 to the n. And now we kind of looks like we're in trouble, right? Because this solution does not satisfy the initial conditions. Usually when we solved quadratic equations, you got two different solutions. Yeah, this is the correct answer. Yeah, I guess you knew it before. Yes, usually we have two different solutions. Therefore, you have a system of two equations to satisfy initial conditions. And usually, a system of two equations has a solution, unless the equations are the same. Here we have two conditions, but only one equation, which we cannot really satisfy unless we guess another solution. And the guess, as D says, is the following. If you have a multiple root, like in this case, then you can actually get another solution by multiplying this original solution by n. Okay, and I don't see any easy way how to guess that this is true. So, but let's check if it works. So let's check to satisfy the equation. If you plug n 2 to the n, you need to check n plus 1, 2 to the n plus 1 equals 4 n 2 to the n minus 4 n minus 1 2 to the n minus 1. Okay, so let's cancel by 2 to the n minus 1. We get 4 n plus 1 equals 8n minus 4 n minus 1. 4n plus 4 equals 8 minus 4 plus 4, 4n plus 4. True. Therefore, we actually do have two solutions. And the most general solution will look like 8 times 2 to the n n plus b n 2 to the n. And now we can try to satisfy the initial conditions. One, so, okay, then what kind of equations do we get? Yes, okay, so a equals 1, 2a plus 2b equals 1. I'm just reading from the chat. Yes, this seems correct, right? So if we plug n equals 0, we get a equals 1, 2a plus 2b equals 1. Which means that b equals, okay, so 2b equals negative 1 equals 1, b equals negative 1/2. Solution. Okay, 2 to the n plus minus 1/2 n times 2 to the n. Okay, any questions? Okay, so what's our schedule? when am I supposed to finish? Do
So,
we usually finish with some exercises, or?
So right now it's like 4:45 Pacific, 5:45 Mountain, etc. Sometimes I say too many time zones, but so right now we can go till around 6 is a good time, around 5 Pacific is a good time. So if you want to, I think you mentioned something about extending this using linear algebra in the description. So maybe if you want to.
Yeah. Okay. So I think maybe that's a good way. So, but first I need to ask. Can you raise you can raise your hands, right? So, how many people have seen multiplication of 2 by 2 matrices before? 1, 2, 3. No. I mean, I will remind it. I just it's nice to know how many people are familiar. Okay. A relation with linear algebra. Yes, so I think probably I'll be able to finish exactly at 6. Let's get back to our equation about Fibonacci numbers. Fn plus 1 equals Fn plus F n minus 1. Okay, so first motivation. Motivation that we want to be able to calculate Fibonacci numbers with very large numbers. For example, n equals, I don't know, 10 to the power 20. Right? If you calculate them up to a billion, you can just do it on the computer by calculating the step by step. In general, we even have a general formula, right? Which has, we have this binary formula, but this formula is not very convenient for calculations because if you try to calculate it on a computer, unless you are doing it with a computer algebra system, root 5 will be, it will not have exact value of root 5. It will have some approximate value. And then when you take it to the power n, there will be more and more error. And this formula cannot be really used to calculate large numbers, even though it's explicit, because you cannot calculate floating point numbers with arbitrary precision. But using linear algebra, you can actually calculate very large Fibonacci numbers using only integer arithmetics and in a very quick way. So let me try to say this. To do it, let's do something which looks a little bit silly. Let's write the equation for Fn and Fn plus 1. Okay, let's consider the following vector. Let's denote it by Vn. Fn. And let's try to write down the equation on the components of Vn. Okay. So first, let me introduce the matrix notation. If you have a vector, if you have a matrix A, B, C, D multiplied by a vector xy, then you get a new vector ax plus by, cx plus dy. So we will consider vectors with two components. Let me mark this is the vector. Each vector has 2 coordinates, and it's in linear algebra, it's convenient to write them in terms of a column. And this is a matrix. And this is also a vector. So you can multiply 2 by 2 matrix by a column vector with 2 components and get another column vector with 2 components. The definition is, this is basically, you can consider this as definition of multiplication of matrix by a vector. Let's try to write down the equation for Vn using the matrix language. So Fn plus 1 Fn equals, okay, we substitute first line, but the equation for Fn plus 1. I was also going to do it with the second line, but actually we don't need it. So it's going to be Fn plus Fn minus 1 Fn. Right, so now you can see that the components of this only use Fn and Fn minus 1. So they only use the components of V with index n minus 1. So you can write down it like this. 1, 1, 1, 0, Fn, Fn minus 1. Okay, so let's denote this matrix by A. This is going to be Vn. And this, by our notation, is Vn minus 1. Oh, by the way, I think for convenience, let's denote all vectors with arrows. Like this. And so we can write down this equation. Vn equals A times Vn minus 1. And also let's V1 equals F, sorry, let's do V0. V0 equals, what's our definition? F1, F0. Oh, I said something that my phone recognized as Hey Siri. Oh, it's that again. Okay, sorry. All right, so V0 equals F1, F0, which is 1, 0. And now how to calculate Fn using this language. For example, F, okay, V, let's say V, I don't know. V1 equals A V0. V2 equals A V1 equals A times A V0. And in general, Vn equals A times blah, 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 V0. Where A applied n times. So it's not geometric. Yes, so I get to answer the question, some sort of geometric series. So it's actually more like a geometric sequence. You'll see in a moment. You do not need to add anything. All right, A applied n times. And for those who are familiar with matrix multiplication, you can write it in the same way. Vn in the following way equals A to the power n times V0. Where A to the n is nth power of A. All right, so let me define matrix multiplication just for those who have never seen it before. If you have two matrices A, B, C, D, E, F, G, H, it equals, by definition, okay, AE plus BG, AF plus BH, CE plus DG, CF plus DH. It's just a definition of matrix multiplication. You can check some properties. For example, A applied to V, where V is a vector, equals A times A applied to V. So instead of applying matrices one by one using this rule that I had somewhere here, you can first multiply the matrices and then apply the product to the vector. There are some other properties which are true. For example, if you have three matrices AB multiplied by C equals A times BC. But you have to be careful when you work with matrices, because in general, AB is not necessarily equal to B. Sometimes it's true, sometimes it's not. But here we're going to be working only with powers of the same matrix. So however, A to the K, A to the L equals A to the L, A to the K. So if you are working with matrices obtained from a single matrix, then you can interchange the order. All right, let's get back to our question. So we have Vn equals A to the power n times V0. And of course, if you know how to if you know how to find Vn, we also know how to find Fn, because Fn is the second component of Vn. Correct? Yeah, Vn is equals Fn plus 1 Fn. Okay, now the natural question. Is there any simple way to calculate A to the n? So is there a good way to calculate A to the n? N is very large. Okay, so you can do it for any n, but let me give an example. For example, n equals 1024, just for the round to be number to be round. All right, how to calculate A to the 1024? You can multiply A by itself 1024 times. That's going to be a lot of multiplications. So is there any way to calculate this quicker than doing 1,000 multiplications? So yes, it will be.
Just do A squared 10 times.
Yes, exactly. So if you do A squared 10 times, it's going to be much more quick. And you can do a similar thing for any number. You just write down some recurrent algorithm. If number is divisible by 2, then you take square of the okay, let me write down it more from this. So A to the n equals A to the n over 2 square if n is even, n times, sorry, A times A n minus 1 or 2 squared if n is odd. Right, so this way, the total number of multiplications to compute A to the n will be of the order logarithm n, which is much easier. So this is the relation. So if you use matrix multiplication, you can reduce the number of operations to calculate nth Fibonacci number to something of the order logarithm of the number you want to calculate, which is much faster than doing it one by one. Okay, so that was the application of linear algebra. I don't know how clear the last part was, but I have to stop here.
All right. So thank you so much for giving a talk today. And if anyone has any questions, feel free to ask them now. Otherwise, I think we will end here.
I can give a couple of exercises if you want.
Yeah, good idea. Let's do that first.
So it's kind of simple.
If you want to send me like a PDF of these, if that's possible, afterwards.
Oh yeah, sure.
On the website too.
First, it's this example has kind of more historical value. There is something that's called Lucas numbers. It's called Lucas, or maybe Lucas Zeckendorf theorem. Sorry, I don't really know what Zeckendorf theorem. Maybe I know it, but I haven't heard about it. I don't know the name. L1 equals 1, L2 equals 3. So instead of starting from 1, 1, you start from 1, 3. And Ln plus 1 equals Ln minus 1. Same equation as for Fibonacci numbers, but different initial conditions. Find the formula for Ln. For every positive integer is the sum of non-neighboring Fibonacci numbers. Oh, this one, yeah. I think I can. I think you can do it by deduction. Yeah, just like Priyashni says, you take the largest number that's smaller than this integer and subtract it, and then repeat this. And if you happen to get, yeah, I can write this down. Let me. 2. Okay. Well, remember that sequence. Let me. Yeah. Exercise 2. Okay. So try to introduce the vector in the same form. Let's say let Bn equals u n plus 1 un. Find, so let's say part A. Find A such that Vn equals A Vn minus 1. And B, okay, try to calculate find the formula for A to the n. Okay, let's say these are 2 exercises. We already have a formula for un, but now you want to use this to find the formula for powers of matrices. This kind of works both ways. Yeah. Okay, so Zeckendorf theorem. Yeah, I can just tell you the idea of the proof if you want. let's say we have some n, some number n. Find largest k such that fk less than or equal to m, right? And then let m equals n minus fk. Okay, so then you can say that n equals fk plus m. And apply the induction assumption. Yeah, so I should say that we start doing by induction, and we're using the second induction theorem. So we assume that we already know this result for all previous numbers. In particular, we know this theorem for m. Apply induction assumption to m. So then m can be represented as a sum of non-neighboring Fibonacci numbers. So m equals, so then m equals, I don't know, f, let's say k1 plus fk2 plus fk, I'm sorry, fk, I don't know, j. Right, and then we can add fk. So n equals fk plus m equals fk plus f k1, k2, f kj. Okay, and now does it give a solution? So all these numbers are non-neighboring by induction assumption. The only possible problem is that these two are neighboring. But if these two are neighboring, okay, so let me just write. So first, fk1, fkj are non-neighboring by induction assumption. We only need to prove that fk and fk1 are non-neighboring. Well, in principle, they can be neighboring. So if fk and fk1 are neighboring, then fk plus fk1 equals fk plus 1. Which means that because fk plus fk1 is part of n, which means that fk plus 1 is less than or equal to n. But then it contradicts our choice of k, because we chose fk here to be the largest Fibonacci number, which is less than or equal to n. And if fk and fk1 were neighboring, then we have a larger number that's less than n. So this contradicts the original choice of k. Okay, and that's the proof. I mean, I wasn't very precise. You have to probably start, if you want to do completely formally, you have to start from induction base and tell which induction theorem you're applying, but I think you got the idea, yeah.
Okay. So is there anything else you want to talk about, or anything, any questions anyone has? Okay.
Yeah, that's all I wanted to say. If you have any questions, yeah, let me know.
So if anyone has any questions, feel free to ask in chat. Otherwise, this will be ending for today. So thank you so much for giving a talk today.
Sure, thanks for inviting me. Yeah.
Yes, and thank you everyone for coming. There will be another talk next week at the same time. I'll send out an email with the topic soon. So yeah, hope to see you all next week.
Yeah, I'll send you the PDF once
Super.
I get it.
And I will post the PDF of the problems on the website at virtualmathcircle.org.
All right, so then thanks everyone.